So great news. As we did in simple linear regression, we can do predictions in multivariable regression as well, which is awesome. It's a little bit more complicated, but the idea is basically the same. You adjust for some more factors, and that helps you to whatever, get a more accurate prediction. You're controlling for more things. So the regression equation that we get after, or the results that we get after running our regression specification in Stata, we've got weight is equal to this intercept term, which should look, the idea of the intercept term is the same as before. It's a different value now. Minus 14.45 times height, that corresponds to the negative 14.45 coefficient that we got out of Stata, plus 0.139 times height squared, which corresponds to the positive 0.139 coefficient that we got out of Stata, plus 9.15 times male. And this allows, and using this, we can calculate predicted weights for a 5-foot woman, for a 6-foot man, by inputting the appropriate numbers. So for a 5-foot woman, in order to get the predicted weight, you would do this. You would calculate 514.62 minus 14.45 times height, which in this case is 60, 5 feet, 60 inches, plus 0.139 times height squared, or times 60 squared, plus 9.15 times 0. In other words, since this person is a woman, the value of male will be 0, and you're adding 9.15 times 0, so you're not adding anything. And you do the same kind of thing for a 6-foot man. You plug in their heights here, and the only difference, other than the value of height, which will be 72 instead of 60, the difference will be that the value of male is 1, because this person in our data set is listed as a male. And so our prediction will have this additional term in it. So marginal or incremental effects follow this idea of a change in y for a change in x. We're looking at a predicted change in weight given some change in height. Now, as before, the marginal effect still equals the slope of the line, which is just the derivative, but the slope changes with height because of that squared term. So just backing up here, this is really easy to calculate the slope because it's constant no matter whether we're at 20 inches of height, 40 inches of height, 80 inches of height. The slope is all the same. But now we can see that this is a little bit different. So if we're at 60 inches of height, the slope is sort of like lightly positive. But way over here, this slope starts to get a little bit steeper. We want to be able to account for that. So let's get back to marginal effects. So the derivative is a little bit more complicated. So just as a simplified example, not using the actual output from Stata here, if we're taking the derivative of y equals 4.81x, derivative of y with respect to x, it's constant everywhere, that's 4.81. And the way that you could interpret that in words would be, for every 1 inch increase in height, the predicted weight goes up by 4.81. And you could append to that sentence regardless of what level of height we're talking about. However, if you have this quadratic term in here, as we do in our new model, you've got the derivative of y equals 4.81x plus x, some x squared. And even though so we do the same thing, the derivative of some linear term like this is just the coefficient. But the derivative of x squared, as you may recall, going all the way back to your Calc 1 days, taking derivatives left and right, the derivative of x squared is 2x. So the way that you could think about that is, for every 1 inch increase in height, the predicted weight goes up, but how much it changes or how much it goes up varies by what level of height we're dealing with. So in our case, the numbers that we got out of our model were, let's just grab this regression. Remember, we had, with respect to height, we had a negative 14 for the constant, for the linear part, and then we had a 0.138 for the squared part. So our derivative then is negative 14.45 plus 2 times x, so plus 2 times 0.139 times height. For a 5-foot person, then, the marginal effect of height on weight is 2.17 pounds per inch. You can calculate that by just plugging and chugging 60 into this equation here. So negative 14.45 plus 2 times 0.139 times 60. For a 6-foot person, the marginal effect is bigger. The marginal effect is an average of 5.49 pounds per inch, which corresponds to the increased curvature in the line that I showed you. We can also talk about incremental effects. Incremental effects it's the exact same idea. It's just that incremental effects apply to binary variables, whereas marginal effects apply to non-binary variables. So the incremental effect of gender, this one's really easy to see because it just corresponds to the coefficient. Men weigh 9.15 pounds more, ceteris paribus, or holding everything else constant, men weigh 9.15 pounds more. However, the difference in weight between men and women might not be fixed at 9.15 pounds at every height. We've only allowed our model to estimate a fixed difference between the two, but it's imaginable that there could be some sort of relationship between gender and weight and height that varies, gender and weight that varies over height. So there's a way to do that. We can run 2 separate regressions. So we can run a regression for women, where we're looking at women's weight here, and then we find whatever their relationship is to height here, and then we've also included age and age squared in this model, in addition to height and height squared. And then we run this other regression for men. We've got height and height squared, and then age and age squared. So the same type of model, but we've just subset the data in order to allow these effects to vary by, the effects of height on weight to vary by gender. There are also a couple of other statistical ways to do that, but this is a somewhat simplified example. And you can tell here that these are actually quite different. So you've got these coefficients of negative 8.51 and then 0.09. And then this is negative 21 and then 0.19. So we can tell with some certainty that the relationship between height and weight is going to differ by gender. I'm going to pause for just a second here.